to talk about the Disco MapReduce framework. So Travis did a great lead in this morning saying that Hadoop kind of is the end all in the MapReduce world. And I found another one, Disco. I don't work in the Disco project, but I do use it from time to time. So when Peter asked me to do a talk on MapReduce, I figured I would go this way because Disco is a Python MapReduce framework. It's actually Python and Erlang. We'll talk a lot about that in a minute and kind of how it all works. But it is a kind of a nice alternative to Hadoop, and has a lot of the same features. So I've got a bunch of slides and some examples that we'll walk through. This isn't going to be interactive. I tried to get some AWS stuff set up and just ran out of time to make it really interactive so people could log in and play with it. But it's pretty easy to set up, so we'll show you that. So to get started, MapReduce, has anyone here, first of all, used Disco Hadoop? OK, so we got some Hadoop people. And so we'll talk a little bit about MapReduce then to get started. As you've probably heard, MapReduce is the OS for distributed computing. Google actually has a patent on it, which is always fun to remind yourself of when you start using this, that any day now you might have to stop or pay for it, but I doubt that'll happen. But it is sold as something that works on large amounts of data distributed across thousands of commodity computers. And I'm kind of throw that in there at the beginning to mention this, because one thing I've actually learned, and you'll see it kind of as we get to the end of this too, is that that thousands of commodity computers part is kind of important for really getting MapReduce, getting the most out of it. But the overall idea of MapReduce is pretty straightforward. You have a data stream coming in with a number of records in it. Oftentimes it's just lines from a log file or something. You take it, the mapping step takes those and returns a list of key value pairs that are derived from each record. There's a possible sort or partitioning step that happens next. Hadoop does a big sort in the middle, as we'll see with Disco. It actually uses partitioning and then an optional sort. But anyway, you take the key value pairs from your map step and bucket them somehow, and then feed all of those buckets onto a reduce phase, which can go through and either sum up all the numbers and give you a single number, or it can actually give you a list back, and then you can feed those lists back into a new map job and chain them together forever and have something that looks a lot like Lisp, but is distributed and big. So that's the basic paradigm. It's actually really simple. If you kind of look at the data flow here, one of the big things with MapReduce is you really are trying to do this in a distributed environment across fairly large across clusters. So looking at the details here a little more, you can kind of see breaking this up into a number of different mapping jobs. The idea here is all the mapping jobs are embarrassingly parallel jobs. So you can operate on the input stream completely in parallel. So you have a bunch of records fanned out to different mapping jobs, which then spit back the key value pairs, partition them, and then feed them into the reduce phase, and each reduce phase gives you a result. And most MapReduce engines kind of give you the results as separate files from each reduce phase, and then use Python or Perl or something to put them back together. And Disco is no different than that. You end up with results from each reducer that you work with at the end. Kind of looking at it from the job distribution perspective, it's kind of what you would expect. You have mapping jobs on a number of nodes. What's interesting is a lot of the Hadoop and Disco both don't require you to have the map and the reduce jobs in the same node. So there's a lot of network traffic that actually happens in between these. There are ways to kind of force things to stay locally, but when you're doing this, it's assumed that the mapping jobs and the reducing jobs may be on different nodes. So the streams are kind of merged at the network level and passed out to different nodes. And a lot of the intermediate results might be stored in the local file system, or the distributed file system, so HDFS or DDFS. We'll talk about that in a second. But the notion of a distributed file system is actually underlies all of these, and that's kind of the foundation. And I think Travis actually mentioned that HDFS is what most people are actually using Hadoop for, is the distributed file system rather than the actual MapReduce part. And the whole idea of the distributed file systems on both the ones for Disco and Hadoop are, you basically take your input files, chunk them up across a bunch of clusters, have a few redundant copies. So you might have 3 copies of each file split up across the clusters, and then it can move your mapping jobs to where the files are. So you usually have your mapping jobs as fairly large, or your files in fairly large chunks. So I think last time I used Hadoop, it was 64 megabytes is kind of the smallest recommended chunk size for HDFS. And oftentimes when I work with this, I have fairly large files in my domain, and I'll just use those whole files. They're hundreds of gigabytes, and you'll just kind of put those across the cluster and then move the computations over to them. But the whole idea of that distributed file system is kind of integral to how this works. Is that you have the idea is that you have fast node or faster faster access on your local nodes than you would if you were doing a big SAN or kind of the other storage alternatives. And there are some caveats there I'll kind of touch on the end too that we've learned from doing this in a number of different environments. But overall, that's the basic idea, and it's pretty straightforward. It's easy to deploy these on a cluster, easy to deploy them on Amazon, and they're pretty easy to work with. So Disco is the one I'm going to talk about for the next hour or so. And Disco is a MapReduce engine built in Python and Erlang, so it's actually not pure Python. The distributed processing part is all handled by Erlang, so they actually use the Erlang core to fire off jobs on all the nodes, and then all the client code is actually done in Python. So you write your mappers and your reducers in Python, and those get distributed out using the Erlang distributed programming environments. And then they fire up local Python instances on the nodes and run everything in Python. But the actual distribution is all handled with the Erlang engine. And it's actually, I've been through the code a number of times trying to track down various installation issues at different times. And the Erlang code is pretty small. I think it's only about 6,000 lines of code. It's pretty easy to track through. And the Python code is about the same too. There's not a lot of, it's not a fairly large code base to do all this, which is kind of what you would expect. I mean, if you kind of think about MapReduce, it's not that complicated. And Python working on, kind of with the lists as lists and tuples as kind of main data types. There's not a lot of, you don't have to write a lot of infrastructure to move data around using those paradigms. So Disco actually, the whole Python idea works really well in here. And when you look through the code, it's implemented a lot, kind of the way you would expect it to when you start writing mappers and reducers, which is always kind of neat to see. It does have a distributed file system called DDFS, which is Disco Distributed File System. And DDFS is a tag-based distributed file system. So there's no file hierarchy. It stores everything as either files or chunks. And you basically, when you load up a file the first time, you give it the default tag for that file. And then afterwards, you can have more tags pointing to those files or the chunks that you're doing. So the example I have here is one that we do. We have I'll talk a little bit about our domain in a second, but we do gene sequencing is what we do. So we have these files with a lot of sequencing reads inside of them. So in this case, I have a bunch of sequencing reads that are stored, and the main tag really is just the instrument run name, so where that came from, and that's the canonical way to get back to any set of reads. But then on top of that, we might have different experiments. We might actually want to tag them by instrument, tag them by the user, the person who put them in. So we can build these nice tag hierarchies, group those by projects. So then when you want a collection of files out of this, you just give it one of those tags, and it'll go through and resolve all the files associated with it. So if you want to perform a map operation across all the sequencing runs in project X, you just say project X as your input, and then it'll take care of finding all the files for you and feed those to the mapping jobs. And it's actually nice. If you've used any of the other kind of column store type databases where you're using tags, it's similar. You end up building these schemas for your keys, that oftentimes have lots of colons inside of them, so you can trace down and use that. But it's a nice way of doing this, and it's pretty easy once you start putting your data in there. So really, this is a simple DDFS example right here. I have a bunch of code examples in here. I'm not going to run any of them, but I tried to get as much in here. And this is loading it. That's just the DDFS command. You can chunk it up. So in this case, we're loading the Holy Grail script just into it. Then you can give it a command. The blobs command shows you what objects are actually loaded into your data store. And then you can use, they have a xcat, so you can actually go and stream the files back to your console. And there's a whole lot of other features you can do on here to manage your files. It does use gzip if you're chunking data. If you're not chunking data, it stores it in its native format, and that's useful to know if you're dealing with, especially binary data. We actually deal with a lot of binary data in these setups, so we don't tend to chunk it. But it is stored in its native format when you're doing that way, so you don't have to worry about lines getting rewritten or anything weird. So a simple example, word counting is hello, world of MapReduce. So if you've ever tried Hadoop or anything else, you've probably seen this example. This is word counting in Disco right here. So you can see, a pointer. Yeah, I do have a pointer. Good. So you can see it's pretty straightforward. You define your mapper, and in this case, it's just a simple generator function. So we have the map. It takes a line in, and there are some parameters, some runtime parameters you can pass around. in this case, we're just going to go and take each word in the line. So we're going to split up the line into a bunch of words. And then for each word, we're just going to return a count of 1. So that's the mapping step. So what you get out of the mapping step is a stream of words with the number 1 next to them. And so what the reduce step is going to do is it's going to take those words and the count associated with it and sum those counts. So in the middle here is where you actually, so you're using, actually we're doing the sort inside here. So this KV group sorted iter is actually going to be sorting the words for us, and then we're going to get one word with the counts out. You can sum the counts out, sum the counts, and that'll give you the total word counts in the document you were looking at. So really nice and simple. It's Python, so it's super easy to read. You can just write it the way you would. All of this lives in one file, so it's pretty self-contained. When you run it, you just create a new job here, give it a name, give it some input. One kind of nice thing is they have a lot of different input types that you can use. So you can put HTTP in front of something. You can put DDFS in front of it to kind of tell it where to get the data from. And so it knows a couple different protocols. So in this case, this is a DDFS load right here, the one that's commented out. So I'm just giving it the Python Grail script tag. So that is the key value pair I used for that one. Or I can just tell it to go get it from the source. And in this case, it'll just pull it off the web. Right as that, for the mapping job, it'll just load it, stream it straight from the web into the mapping job, and you don't have to use DDFS at all. And then you set up the map job, the reduce job, tell it to save some results, and then just wait on it. And when it's done, you have a result iterator that you get out and just print them out. So these are the results that came out of this run. So you can see, if you just look at the top ones, there's all the args from the script, which actually I thought they said arg more in the movie, but they did say it a lot of different ways. So. So that was an interesting thing in there. And then you can see the word they actually sorted by count. You know, the is almost always the most common thing when you do word counting. And then Arthur, you know, the actual label they used for the script lines was the next biggest one. So that's a really simple example of using Disco. And really, that's actually all you need to know to do most Disco applications. Right there is just write a mapper, write a reducer, think Python when you're doing it, and the whole system handles everything else magically for you, which is really nice. I'm going to do a little aside here and just kind of catch you up to the domain I come from, because the rest of the examples are all going to use stuff that I work on daily. For me, it was a lot easier to just take a lot of stuff we're already doing. So I work in biotech. Next generation sequencing is what we do a lot of. Is anyone here in biotech or sequencing? OK, so one person. So really quick, the stump speech for this is really simple. We did the Human Genome Project kind of throughout the 90s, about 10 to 12 years at a time, thousands of sequencers, billions of dollars, generated coverage of one human, and only about 7x coverage of one person. So we have about 21 billion bases were generated in that project. Today, we can, it's a little different. So we have high throughput sequencing instruments came on the scene around 2006. And the original ones kind of took about 2 weeks, generated about the same as the Human Genome Project. Today they're doing about 100 to 200, all the way up to 600 gigabases of data per single run, about $5,000 to $6,000, depending on the discounts you're getting. There's benchtop ones too now that basically can do similar things, actually do way more than the Human Genome Project in about 4 hours turnaround time, single instrument for about $500. So this has really changed everything, but what's interesting about this is it's just the sheer amount of data. So if you can imagine 100 gigabases of data is 800 gigabytes of A's, G's, C's, and T's right there. So you're getting very large data files off the instruments. We see a couple, when we're running the big instruments, we can run those 4 times a day, and we can generate 4 or 5 terabytes a day off these instruments, just off of a single instrument. So it's a lot of data. Kind of give you an idea of what the data actually is. It's over here on the edge. So if you kind of think about the way sequencing actually works is you take your DNA in your cell from your sample, you fragment it up into a bunch of little pieces, a couple hundred bases long, and then those are what you actually sequence. And then you have to put all those back together. So what you get off the instrument is actually a file that looks exactly like this, that has a little label for each sequence that it found, along with the actual sequence that it read. So you get basically all of these fairly short strings, usually 50 to a couple hundred bases long is what you get for each read off the instrument. And then all of the algorithms that you do afterwards go and put those back together and tell you how they actually map back to the human genome reference or whatever species you're working on. So it's a real big data problem. And I say big with a capital B because it really is, we deal with terabytes on a daily basis. So it's a lot of data, and it's one of those ones that there's no way around it either. The amount of data we have to generate is driven by the biology. It's not driven by what the instruments can do or anything else. If you want to ask a specific question on a human, so say you want to find all the variations between you and the reference, you have to generate about 15 to 30x coverage of your genome. So you're right away looking at, kind of that 45 to 90 gigabases of data that you have to generate, which when you're actually working with it, it explodes a little bit. So you've got a couple hundred gigabytes of data per run that you're working with. And we can generate that fairly quickly. This is kind of a slide from showing people what our instruments can do, which is actually getting better and better every month. And that's kind of my point here, is that it's probably better just to run away now and forget about this problem because there's just too much data. But it's we do get a lot of data, and it's kind of fun to work with it. So I'm going to use, for the rest of this, I'm going to use some sequencing data just as kind of examples of how we can do different things in Disco. So this is going to show some techniques in Disco, but also, kind of show, it's not going to go really into biology at all, but we'll talk about some of the data. You'll see some of the data in here. So the first thing that you'll kind of notice is if you look at the files I showed you before, the sequencing data comes off the instrument. It's not single line based, and a lot of most of the default for MapReduce engines is just to feed you one line at a time. And since each step in a map phase is essentially has to be an atomic step, you can't really remember what the line you saw before was. A lot of the data that comes off the instruments actually spans 2 to 4 lines depending on the format we're using. So the first line is the ID. Then in this case you get the sequence information. Then you have a plus, and then you have the quality information. So you actually have 4 lines here that is really what a single record is. So if you want to work on this using Disco, you'll have to write, you can write a new input stream reader that will actually go through and take this, pull out every 4 lines, and then return it as a tuple to the mapping phase. So now the mapping phase, instead of getting a line, is getting a tuple that has the sequencing data reformatted in a way that's easy to work with. So taking in the 4 lines up here, and then returning the tuple right here, and then you end up with a stream of single tuples that have all the information that you want to work in. So using the custom input streams is kind of the first thing that you'll find yourself doing often if you're using Disco, and have anything other than like really straightforward log data that you're parsing. If you have complicated data that works in that. And I'll have an example in a little bit that shows how to do this with binary data too. So if you can work with pretty much anything you want. And it's really just how clever you are on writing your input streams. So the next thing is that sorting step that happens in the middle. And this is kind of where Disco differs a lot from Hadoop. So Hadoop by default does its mapping phase, then all of the data is pushed into a sort phase, sorts all the data, and then gives it back to, and then feeds the sorted data into the reducers. Disco decided to do it a little differently. They don't actually sort in the middle. Sorting is completely optional, and by default they don't. So they give you all the keys unsorted. So you saw in that first example with the word count, I was actually sorting them kind of as I got them in the reducer. And of course, if you've got a very large data set, you probably don't want to do an in-memory sort. So that's not always an option. But the other thing that's worth noting is when you're working with the mappers, normally everything gets fed to a single reduction step, unless you have a way of partitioning those streams coming out. So, and this is what the way that Disco does it is it has a partition step in the middle. So as soon as the map step finishes, so I'll walk through this in a second. You can basically feed the key from the mapping step into our partition function, and then return an integer, and that tells you what partition you should be in. So what it'll do then is it'll create the number of partitions you have. It'll create a reduce job for each one of those partitions, and then so you can basically do do data parallelism on your reduce phase too, as long as you understand how to partition your data. So in this case right here, what I'm doing is I'm just taking all the reads off of the instrument, and we're going to find the frequencies of bases at each position in the read. So in this case, the reads were off of an instrument that only produces 50 base pair reads. So we want to see, how often do you see an A in position 1? How often do you see a C in position 1, and then a G and a T in position 1? And you can actually, there's the results right there. But it's pretty straightforward. So the really simple way of doing this is for the position, I wrote a map function that goes through, and it just takes the record. So it takes the sequence coming in. That's the entry 1 in the tuple that I fed is the actual sequence. And it just enumerates the position and the base and returns position and base into the stream. So this is kind of like the word counting, except we're feeding the position along with the base. And then what I do is figure out how many partitions we're going to do. That's what the NP is. And then the key it gives you is the first thing here, is the first element in the tuple that we returned from the mapping routine. So in this case, it's going to be somewhere between 1 and 50. So just kind of modding that by the number. So if I give it 50 partitions, we'll actually have 50 reduced jobs that'll be fed into here, and then every position will have its own reduced job to go and figure out the base frequencies at those positions. And each of those reduced steps then will get a base out of it and the position. And if it's actually sorted that way, you'll actually see all of them. In this case, I think I have it set up to handle seeing any number of positions in here. So this is kind of the more general case right here. But then it just goes and it counts for each base that it sees. Every time it sees one at a position, it just adds a count to it, and you end up with the nice summary plot here. And if you've ever done human genomics, you'll kind of know that this is pretty much the way that bases are distributed across the genome. And what you can see here, this is actually more for internal QC. At the beginning of the reads, you can see some bias in specific directions, and this is just kind of an artifact of the way that the sequencing actually works. That you preferentially sequence when you go and split up the fragment things. You kind of preferentially fragment in certain areas, and you can see that a little bit here. What's going on, and sometimes at the end too, you'll see things happen there. So that's basically partitioning and an example of how you would use it in here. So for this talk, I wanted to go a little further than what we do. So we don't use Disco all the time, but when we do, we have it running on our internal clusters. And I wanted to see how can we move this into the cloud? Can we actually set up something like Amazon's Elastic MapReduce using Disco? If you kind of Google Disco and Amazon, you find 1 or 2 hits of people who tried it, but they never posted anything else. And on the Disco page, it says, sure, you can do it, but doesn't give you any examples of how to do it. So I wanted to figure out how to actually set up Disco on AWS and be able to create clusters and use EC2 to set up Disco jobs and then pull data from different sources and actually process them all on the cloud. So, so what I did, is anyone here who's used EC2 before? Okay, and Star Cluster, have you guys used that? So this is what I ended up doing. Just want to see who else knows, because I was learning all of this as I was doing this. So I'm always looking for more feedback on the right ways. But this was actually really easy. So Star Cluster is basically it's out of MIT, and it's a tool for setting up clusters on EC2. So what it'll let you do is you create your machine. You can create a custom machine image, and then you can basically tell it to create a cluster for you. And it'll go off and you tell it how many nodes you want. It just allocates everything for you. It's actually a nice tool. And one of the other reasons I use it here is Star Cluster is all written in Python too. So we're actually showing how to do an entire entire MapReduce stack using pretty much entirely Python tools. But when you're working with, so if you worked with machine images on Amazon, Amazon has a bunch of default machine images that kind of have some basic things on it. Star Cluster provides a couple machine images that have a few more scientific tools. So IPython is actually available on there, as NumPy, SciPy, and there's some other tools that are common scientific computing tools that people use a lot are on their images, but Disco wasn't on their image. So the first thing I did here is actually created an image that had Disco and the few other bioinformatics libraries that I needed to use on here. And it was pretty straightforward. They actually have just a little command line tools where you go fire off a single node instance. So that little S1 is telling us to do one instance. Tell it what you're using as your starting instance. So I just used one of their default ones as that, or as their base AMI. And then the instance type is actually the size of the type of instance on the virtual compute resource you're using. So they have like the small ones and the large ones and the extra large and the high memory. So that's Amazon things right there. So you can kind of pick what type of machines you're going to target on here. And in this one, I just used the small ones. I was trying to keep the price down on all of this too. But it's pretty straightforward. So you create a single node, then you just log in, and then you log into that node and configure it however you want. So in this case, I logged in, installed Disco, installed the other things. Then you basically tell it to create an image. And Amazon has 2 different data stores, or 2 different ways of storing these. You can store it on S3, which is kind of the standard way of storing a lot of data on Amazon, or you can use these EBS images. And those are a little faster. So I used one of those for this, and so I have an image now created for the Disco that has all of Disco installed, and now I can go create Disco clusters out of it. So at the bottom here, you can kind of see the example for starting a cluster using star cluster. And again, it's really, really easy. You just give it the start command, tell it how many nodes you want, tell it which instance type to use, and it goes and does everything else for you. And then you can SSH into it and have fun with it. So once you've got the cluster up and running, you want to go ahead and get Disco up and running on it. So there's going to be a few more steps that we'll do to set up Disco. The first one is I do here is I actually and this is kind of showing some of the configuration and how you can configure. So Disco has a bunch of configuration options that you can go through. You can tell it how many nodes to use for redundancy. So if you're copying files out to DDFS, you can tell it to do 3 copies or 1 copy or 10 copies. You can tell it. There's a lot of different commands in there. But one of the ones is where all the default paths are. So I am actually just going to change the paths in here to use when you have an Amazon image, you have a couple different default mount points. One of them is the actual image that you mounted, and then you've also got kind of your default scratch page, which is most likely the local drives on the node that you're running. So you get with a small instance, you get 160 gigabytes that you can work with. So I tell DDFS to use those. The one key thing when you're doing Amazon clusters is those are transient. So if you're trying to use this as a permanent file system, you'd want to set up a slightly different strategy than this. So this is just using the transient drive. So every time I ran this, I would have to reload all of my data over to it. And then you create a mount point. So create the mount point for the DDFS. So Disco, obviously, since not everyone knows about it, does not nearly get the developer resources that Hadoop does. So there are a few little bugs that I've ran into every time I've installed it, and I keep meaning to post the mailing list and help them out on that. But this one gets me every time, is that as soon as you point your data to somewhere else, you actually have to go through and create these DDFS directories by hand, and then everything works fine after that. And then to get Amazon working, so the control panel for Disco is a web app. So you have to be able to point your web browser through to it, and they use port 8989 as the default one. So on Amazon, you have to update your security group to allow inbound traffic from that port. And that's a pretty simple step there. And then once you've got that set up, you can go ahead and fire off Disco. And it's really simple. It's just kind of like star cluster. It's the Disco command, and then you do start. And as long as things were set up right, it will just start and run. And then you can hit the web app and go see. And right here, you can see when you start it up the first time, what you end up with is a Disco instance with a single node on here. You can see it tells you how many. It gives you some statistics. Here's the numbers there will tell you how many jobs are running in different map and reduce jobs, and I think failed jobs is the third one. And it'll also tell you how much storage you have available on your DDFS volume. So that little green bar will start filling up as you start adding stuff to each node. So you can use that for monitoring. But one node Disco cluster is not that interesting. So you'll want to go and add some nodes right away. So in Disco, the way you do that is you just go to the web app, and over to the configuration panel, and you just add some nodes. So in this case, the naming convention on the star clusters is node, and then three numbers. So node 0, 0, 1, all the way up to however many nodes you've allocated. And Disco lets you use kind of a range notation there, so you can go node 0, node 1 to node 3, and it guesses the naming convention and fills in all the nodes for you. And when you do that, you hit the Save Table button, which I've forgotten to do and never understood for some reason. That didn't make sense. I lost that the first time. I'm like, where are all my nodes? But their user interface isn't the most thought out one. It's again, it's simple, it's nice, and once you've done it once or twice, everything starts to make sense. But it also supports blacklisting for Disco and for DDFS. So if you want just dedicated compute nodes, you can tell it you basically blacklist a bunch of nodes and tell them not to store files on those. You can do the opposite if you want dedicated storage nodes for that. So there's some things you can do for configuring your cluster. But if everything works, you end up with on your status page now you'll see all the nodes that you have allocated. So that's basically it. Once you have it up and running, now we've got a fully functional Disco installation running on EC2. So what can we do with it? Let's go ahead and actually, I'm going to walk through an example now of processing some more big data. So one of the neat public data sets on EC or on S3 is some data from the 1,000 Genomes project. So the 1,000 Genomes project is a big research project where they're going to go fully sequence 1,000 individuals and just have all of their sequence data available for research. So it's looking for variations are the big one they're looking for. But there's a lot of studies that you can imagine being done on that amount of data. It's a lot of data though. So they've posted 7.3 terabytes of data on S3 that anyone can go and play with. And as I learned very quickly, you really have to understand sequencing and what the data is to actually work with any of the data. So it made a great press release when they did it, but if you actually look at the data, it's kind of a low-level sequencing data format that's hard to work with unless you've used it before. It's actually all posted as binary files, so these binary alignment files, which so what they've actually posted on here is they've taken all of the data for the individuals, mapped them back to the human reference, and they tell you where all of the reads from the sequencing instruments map to the human reference. So you actually have the results of the first passive analysis is what they've actually made available to us to work with. And it is a binary format, so it's binary data. So we're going to have to figure out how to work with binary data on Disco in this case. So as a really simple example, what I wanted to do is just basically take all of the genome data they've put on here and just see what's the coverage look like for all the chromosomes. So how would we go ahead? How do we go through and take the mapping data, do a simple MapReduce pipeline, streaming all of the BAM files that they have, and then create a coverage map of the genome to see if we're actually, covering all of what we would expect to see in a genome. And actually, it's not. I changed it from SNP to coverage, so the slide's a little bit wrong, or the title's wrong. But it's pretty straightforward. Again, this looks a lot like the word counting example. And all the other ones. The coverage map is really simple. Assuming I'm getting a record out of the binary file, and we'll talk about that in the next slide, how we actually did that. Basically, I get the reference and the read passed to me. Those are the two things that are passed into the map thing. So the reference is what chromosome it hits. So that would be chromosome 1, 2, or 3, or X, Y, or M, or MT. Is the way it was annotated in here. And then each of those read records is going to have a position where that mapped to the chromosome. So the first thing, what I'm returning as my key is I'm returning the chromosome name and then the actual coordinate on that chromosome that the read mapped to, and then I'm returning how long that read actually was. So depending on the instrument platform you're using, you might get 50 base pair reads, but you also, a lot of them have variable length reads that you're getting out of there too. So you could have up to 800 bases possibly in a read. So that gives you an idea of what the overall coverage would be. So you can use the start position and the read length to figure out the depth of coverage at in that area on the genome from that particular read. So for the partitioning function, I actually just partitioned it kind of logically using the domain model here, and just partition it based on chromosomes. So if it's chromosome, I just use simple numbering. X24, Y25, mitochondrial was 0. And then for the 1 to 23, just used ints on there. So that comes from the cutting and pasting I did to make this fit on the slide. It's coming from key. So in here, it's key. So it actually is key in here. So good catch. See, someone's reading the code here. But yeah, sorry about that. The key is the so if you see where I build the key up here, I put the chromosome name, which is coming from reference, in the position. So right here, I'm splitting it, and that right there should actually be CHR. But this was copying and pasting and reformatting to make it work on here. But yeah, so that's where that's going. So this will create 26 buckets that the various chromosome data will go into. So in the end, I'll have 26 reduced steps here and 26 sets of results that I get out at the end that will show me the maps. And then the reduction function is pretty simple. This actually hits an important thing in Disco that's worth talking about a little bit. So you'll notice I'm importing NumPy inside the reduction function. So one of the requirements in Disco is that the map and reduce function should be essentially kind of pure functions. You really don't have any access to any external data, so there's no globals. You don't know what modules can be loaded. So if you're going to use a module, you have to load it inside the function when you're working on this. So you'll see in here I'm importing NumPy directly to work with the data and create and do it. So that's just one of the ways that it's set up. And it actually is the way under the hood, the way it's implemented is it actually takes the client data, essentially packages it up and ships it all over and then fires it off in a so it doesn't have in Python interpreters running. It just takes the running state from here and moves it over there, I think is how they're doing it. So kind of like what IPython does in a way. But they've been really trying to make it so you can have very minimal Python installations on the nodes, or none at all, and then be able to move the actual code over there, execute it, move self-contained code from the client side over to all the nodes and do it. I wish I understood a little more about how it's doing, but that's one of the important things to know in here. And kind of another caveat on that is the map functions, really get called once for each line. So they do give you this params thing, and you are allowed to stick some persistent data in those. But there are some constraints on that too. So the parameters data is really persistent to the actual node that you're working on. So it's not globally persistent data, so you can't use that to like do communication back and forth between map jobs. But again, that goes with the whole spirit of MapReduce, is that all the map jobs should be independent jobs. The reduction jobs are actually fairly long-lived. These usually don't get restarted. You feed the stream coming into it, and these will live the whole time. So the way I actually create the chromosome maps here is I have just a dictionary that gives me the sizes, or roughly the sizes of all the chromosomes, and then I go ahead and create an array for those that just has I use zeros, create an array that I have just counts at every position in the chromosome. So these can be fairly large. The largest chromosome is 250 megs, so that can end up being about 2 gigs of data that you end up allocating there. And actually on the small memory nodes, I had to drop these off by 3 orders of magnitude to make it fit in the RAM on the nodes. But that's the basic idea, is create an array here, and then stream in all the position data that comes out of the mapper. So I pull out the chromosome, find the I have one per chromosome in here, so what I'm doing is each reducer will know what chromosome they're working on, so they'll only get data from the same chromosome. So then when I'm going through here, I pull out the position information and just go ahead and using just slice notation, start at the position and position plus length, and add a count to there. And now we kind of know what the coverage at that position on the chromosome was from this. And then when I'm done, I just return that as a string. So it kind of works with the ASCII formats that they like to ship around from these. So the big thing I kind of left out here, which goes into the next slide, is this is all binary data. And this is one of the fun things, I think, with the MapReduce systems, is trying to figure out how can you work this with any type of data. And usually you can think of how, if I have my data in the record format I'm used to working, you can think of a mapper that you'll do, and you can think of a reducer. But oftentimes, if you're working with scientific data or data from arbitrary sources, there usually is a record format that you're dealing with, and if it is binary, you got to figure out a way to actually work with that. And in this case, it was also data stored on S3, and I didn't really want to copy 7 terabytes of data over to my local nodes, because that would have cost me a lot of money. Instead, I wanted to kind of move the BAM files over one at a time, cache them, stream them as binary files, and then get rid of them right away. So the way the reader that I ended up writing for this, it looks like this. And again, you can see the importing inside the reader to get the temp file and the PySam, which is the library, the domain-specific library I'm using. One kind of neat thing with Disco is all of the mappers, reducers, readers, a lot of these can be kind of chained together. And readers are really nice to chain, because what you can do is you can take advantage of all of their infrastructure. So in here, the S3 files are just web addresses, so HTTP strings that tell me where the file is. So the first thing that they'll actually do is they'll use their HTTP reader, and then I get a stream from that HTTP reader that I can work with right here. So they're taking care of getting the data from the web or from S3 for me already. So what I do is to make this work with the binary data, I just create a temp file, take the data from the stream that they're giving me, read it, dump it to the disk, and then open up using the SAM tools library, the PySam library. I open it up, and this takes care of all the binary, unpacking the binary data for me. And now I just have a nice iterator of every single read in the file, and I just yield these. So now my reader is almost a map step in a way, but it's instead of doing a key value pair, I'm just returning the single lines that and they're not even lines in this case. It's really just a tuple that contains the reference name and the read. So Disco makes it kind of easy to blur those lines between mapping and reading and reducing, but it also gives you a lot of flexibility. And if you're kind of used to building pipelines like this for data, you can kind of see a lot of different ways in Disco where you can chain a lot different pipeline steps together, and kind of massage your data kind of independently at each one, and get around some of the either different problems that you run into, or just work with different data types. And internally, it actually does, Disco does pass everything around as these lists that you return from here, so those don't get changed too much as they're going through the system. So that was actually one of those undocumented features I did find, is if you don't return tuples in your yield statements, it actually crashes and doesn't explain why. So they actually do assume that the readers after the first one aren't working on line data, instead they're working on tuples, which was an interesting one. But anyway, so with this, basically that's what I do, and then when I'm done, I just close my two references to the file I created, and then temp file will go ahead and delete those for me. So I never fill up my local space at all with the 7 terabytes of data. Instead, I only have the working data that I've got. And you'll notice too that I skipped DDFS entirely for this particular example, and that was in large part because there was 7 terabytes of data on the other end that I didn't want to have to push in and pay to store. So the final thing for this one, basically, you saw the mapper, the reducer, and the reader. And what we to put it all together, here's what the job looks like. In this case, I give it the list of all the locations in S3. So there were 500 BAM files in the final example that I used here, and give it the reader, tell it how to partition, tell it how many partitions. Give it the mapper and give it the reducer, and then fire it off. And it runs for a long time, and then I get back the results for each chromosome and just write those out to a text file. And I was able, so I'll talk a little bit about some of the things that can go wrong in here, but let's see, here's one of them from chromosome 12 for one of the data sets. So you can actually see this is, there's a big spike in coverage in one area, but if you know much about kind of genomics, what you can actually see here is that, there's always a region in the middle where what's the name? I'm pointing to one of the guy who raised his hand for biotech. The centromere, thank you. So the centromere is at the beginning, is in the middle of the chromosome. So yeah, if you picture those two cartouche type things that meet in the middle in the pictures that you see, there's the centromere area in here, and it's actually an area of really low complexity. And it's also, in this case, it's an area that actually picked up a lot of reads. It's probably just a priming bias, but overall, you see, nice coverage across this whole chromosome right here. A little bit more at the end. Again, the characteristics of the ends are kind of like the characteristics in here. But if you were to see that for all of them, you'd see the similar pattern where you have, the two sides, the two arms on the chromosome, and then the gap in the middle, and fairly good coverage all the way across.
Can you explain what the X and Y axis?
Oh yeah. So the x-axis here is chromosome position. So this one is going up to add 120 million, or about 130 million. So these are actually, I binned it a little smaller to actually get it to work on the small nodes. So this is 130 million or so long for the chromosome, and then this is the number of counts that were observed at that position. So it goes basically, from 0 counts in some areas all the way up to, kind of around 200 counts for this particular data set. So that's the amount of depth that they were able to get out of that sequencing run on this chromosome. So a count is basically when you have so if you picture with the sequencing, when you fragment up the source material, those fragments are all fairly short. So each time one of those fragments maps back to the chromosome, you get a count, and it's just I do it based on the length of the fragment that mapped back. So you get that's how you end up with the peaks there and the depth. So it's a simple example, but it's that type of workflow is fairly common in genomics. Is just going through all the reads, computing something simple, and looking at some results. But a few things I use MapReduce from time to time, and I kind of wanted to take advantage of this to talk a little bit about that too. Kind of what I found it's good for and what it may not be. But Disco, first of all, is a great alternative to Hadoop. I don't know if you've ever tried to install Hadoop. It actually takes time. And there's a lot of configuration stuff you've got to do to make it work. Disco generally installs a lot cleaner, assuming you don't run into some of the few bugs that seem to get fixed. Every now and then there's a weird bug, and that is one thing I know because I've been through the code a lot the first time I did this because it didn't install very well the first time. And there were a bunch of little issues that they had, but at the same time, I got to see all the code for it and doing that. And they actually have done, it's a fairly clean implementation. It makes a lot of sense if you're trying to write a distributed processing engine. What they've done here is actually really clever. It's a really interesting way they did, especially the way that they use Erlang and Python together. So the reason they use Erlang because by default, Erlang is really easy to distribute across a lot of nodes. And it has the whole distributed computing infrastructure built in. So you kind of have your master node that as long as it knows all the nodes, it can fire off the infrastructure. And they've done a really good job of making sure Python plays very well on top of the Erlang infrastructure. So I think the way they've set it up is actually pretty clever, and I'm kind of pointing at you guys out there because it's worth looking at the architecture they did for some of it, for doing that. And it's not too far removed from how IPython does some things either. So it's kind of a neat little system. I don't know how many people actually work on it, but as far as I can tell, it's only a couple guys at Nokia that do this. And so it actually was developed at Nokia, and they use it internally. Another interesting thing I've learned doing it, so we have a number of different clusters. Some of them are kind of the traditional commodity clusters where you have 3 terabytes on each node, and you have either 10 Gigi or InfiniBand between the nodes. And that works well, just fine. But we also use this on just traditional HPC storage, so the SAN system. So we have some HP systems and then some data direct network systems that we've run this on. And it actually, as long as the disks can feed all the nodes fast enough, it works really well too. So you're not really. I actually found on the real high performance storage systems, Disco runs a lot faster than it does on commodity clusters when you have the same number of nodes. And a lot of that comes from just HPC storage is really, really fast. So our DDN systems give us about 3 gigabytes per second, and that's bytes, not bits, 3 gigabytes per second throughput to the nodes versus if you even have a good RAID setup on a commodity node, at most you're going to get kind of 100 to 200 megabytes per second. So we're able to get really high throughput on the big storage systems, but then still use MapReduce as kind of more the processing. So then you don't even have to worry about DDFS for the storage. You just use your HPC storage system, and then if your problem fits well in the MapReduce framework, you can just use that on top of it. So I've done it in both settings, and I tend to actually use the HPC storage use case more often now than I use the DDFS when I'm doing this. But on that, I was kind of new to the whole tag-based file access, and I like the way they do that. That actually has been a great way to organize data and kind of do those ad hoc databases, which if you're playing with any of the other column stores, you're kind of probably getting used to naming all of your data using those conventions. But it's really nice the way that they allow you to have a tag hierarchies. So you have the tags pointing to each other that can ultimately resolve down to the file, so you can group things nicely. And Disco also has this thing called DiscoDB, and I didn't talk about it in here, but it basically is a tag-based data store, so kind of to compete with all of the other column stores. And they claim it's really fast, but I've never set it up, so I can't say anything other than it does exist, and it looks promising. On the MapReduce side, I know this is a Python and MapReduce talk, but it's definitely a good and a bad thing I found. It definitely certain problems. It's I always liken MapReduce to GPUs. If your problem looks like a image or a graphics pipeline, a GPU is a great option for you. If it doesn't look like a graphics pipeline, maybe it's not the best option for parallelism. And MapReduce is very similar to that. If your problem looks like a streaming data problem where you have a clear map step and a clear reduce step, it's a really easy way. I mean, you saw the mappers and reducers I was able to write. They're really simple, especially using something like Disco where you can just keep everything in Python in a single file. It's very easy to work with. Of course, Python is pretty straightforward too, so oftentimes your pure Python code that doesn't use MapReduce looks a lot like your just straight MapReduce code. So you can, and that's kind of the next point there is that when we first started using this, I did a lot of performance tests to kind of figure out, are we actually gaining anything from MapReduce? Because my goal with MapReduce in our environment was to make it easier for biologists to work with the really large data. They were struggling with kind of loading all of these reads into a Perl hash and watching their program crash after about 3 hours of trying to load it. Happens every time someone starts doing this. That happens. So my goal with this was to see is can we give them an abstraction that's a little easier to work with that hides them from a lot of the common problems you run into when you're working with these data files that are a couple hundred gigabytes in size. And so it does make it easier if you can get everyone to learn Python. And as we learned, a lot of analysts actually learn R instead. So, but I've been working on transitioning them over to play with this. But on the flip side, when we did the performance test, we ended up finding that the simple batch processing was for almost every problem was significantly faster. So if you have a job scheduler, if you have Python installed all the nodes, and you don't mind doing a little bit of data parsing on your own end, I found that it was usually 20x faster to do it just with pure Python than it was to use the MapReduce frameworks. And we tested this back and forth with Hadoop also, and found that generally to be true. And doing some deeper analysis, so I did some profiling on there to find out what was really going on. And it's really simple. It's just the abstraction penalty of those map steps. So if you look at getting a single record in each time, and if you actually go and just do a trace on the Python stack, you've got 20 or so function calls leading into that have to get executed every time for you to get every single data element. And Hadoop has the same type of stack on the Java side in a lot of cases. Whereas if you're just working on the raw file streams off of the operating system, you basically have the I/O buffers and that's it, and then they're giving into Python. So you have no your abstraction penalty is significantly less when you're just writing simple batch jobs. While I think that while this is a neat programming paradigm and it works well in commodity clusters, I think it's always worth looking at what resources you actually have available and seeing if the overhead of something like this is actually worth it, or if you're getting the benefits. It's kind of a good and a bad thing, because the one thing I have learned is every time I play with this, you get sucked into it. It's like when you pull out Scheme or Lisp, you get kind of sucked back into that world and you have a lot of fun with it for a while, and then you come back to reality. And I find that this is just as intoxicating as that. It's really fun to start thinking of everything in terms of map and reduce. So it's a neat paradigm, and I think as more people use it, we might see more improvements in making those stacks run a lot faster. But every now and then, you do have cases where if you really have petascale data and you want to distribute it across a warehouse of computers, this is not a bad way to process it. And I think I don't have any context into how it's been used at outside of what papers published at Google or places like that. But that seems to be where the use case where it actually is really useful, is when you do have 2,000 computers and you actually have a couple petabytes of data spread across those, and there's no other way to get at it easily. When you have, even with what we're doing, when you have 10 or 20 terabytes of data, if you have access to it on a decent storage system, you can operate on that just fine in Python as long as you're kind of smart about it. And that's where we were seeing the big penalties for it. But I can see if you've got 2,000 nodes and you really want to do a petascale question, this is probably the easiest way to do it. So that's kind of what I figured on it. I got some references in here. But Disco, I definitely encourage, if you want to play with MapReduce and like Python, it's a lot, like I say, it is intoxicating when you get it set up and you fire off 20 nodes, and especially when it's working at Amazon or places like that. It's kind of fun to play with it, the MapReduce star cluster. And I was kicking around ideas too, because there were some things I started the whole Amazon part of this on Tuesday, thinking that I would actually have a lot more running by now. And I have some open things that I think would be a lot of fun, because when I started the Amazon one, I went to see, has someone done this already? And of course, no one had yet. So it'd be fun to take what I've got started and just clean it up a little bit and make a public AMI out of it, so anyone else who wants to run Disco on Amazon can do it almost as easily as they can Hadoop. So if you've seen, Amazon has their elastic MapReduce that is just a kind of a front end for Hadoop, so you don't even have to do any work to set it up there. We can't quite get that far with Disco, but we can make it a lot easier for people to try it. So I think for Hackathon tonight, if anyone's interested, I think it'd be fun to go and I might just do this with my time there and get this thing made public, so we can put it out there, put a little documentation as to how to do it. I've never done star cluster plugins either, but that would be an alternative for doing this. It might actually be a little easier with star cluster. You can actually install a bunch of stuff as the cluster is being set up, so that would be another way to do this. And another one too, I don't know if anyone's used EBS volumes, but it'd be fun to try. That's their kind of you can have up to a terabyte of kind of block level data storage in Amazon. And I'd like to figure out how to set that up on here so you can actually have your DDFS clusters persistent. So the way I did it, it used the transient storage, so we lost, every time I shut down the clusters, I would lose the data. But I'd like to figure out how to do it so you have one EBS volume per node, so you can actually leverage the whole DDFS file system for more long-term data storage. So those were some kind of next steps that I think would be fun to go on this thread. But all right, well, thank you, everyone. Thank you.